So thanks so much, Josie and Fumia, for the invitation. It's great to see you online. It's better than nothing, so it's great to see you. And I see many friends online, so it's great to see you all. And I thought for today to present a bit some work we did with Auke Ijspeert in the framework of an HFSP project, which is about this very nice interaction between sensory feedback loops, reflexes, and CPGs in locomotion. And we published that in Science Robotics last summer. So let me go over that. So it's gave a perfect introduction because it's really related to locomotion, which for me is the most beautiful example of embodiment. And the more I do robotics, the more I'm really impressed by animals. So here, if you look at this running dog, of course, its nervous system is solving a very complex control problem. And everything is really dependent on the embodiment. So the fact that we have the spinal cord circuits that can benefit from nice musculoskeletal properties is really a key component. And as well, of course, the spinal cord circuit itself is super important. So the multiple reflex loops and central pattern generators, which I find very interesting circuits, these neural oscillators that you can find in the spinal cord circuit that can by themselves produce open loop patterns for locomotion. And obviously you have all the higher part of the brain that are super important, but today I really would like to focus on this interplay in the spinal cord between what I would see as feedback mechanism, the reflexes, and feed-forward mechanism, which will be these outputs from the neural oscillators, the CPG. And it's very hard to decode how they interact because it's a complex interactional process. But I think modeling can help to do this. So in my lab, we have been interested in this for quite some time, and we have a bit the hypothesis that during evolution, we have a bit switched from more feed-forward driven locomotion, more CPG driven locomotion in lower vertebrates, to more and more feedback and sensory driven locomotion in mammals. So of course it's a bit hard to test this, but to test this hypothesis, we like to make numerical models of the spinal cord circuits and test them in closed loop with real robots. So that's what I like to present today. And I will focus mainly on the swimming part. So briefly, just to show the beauty of the spinal cord circuits and the CPGs in particular, this is a bit older work, but here we could demonstrate that in principle, a properly coordinated system of coupled oscillators can generate beautiful patterns in open loop to do locomotion. And for instance, here for simulating the salamander locomotion with a robot, we could demonstrate at least that the CPG is perfectly capable of doing tuning of gait, speed, and heading. And basically, that's the beauty of more the feed-forward component in locomotion. But obviously, in animals, there is sensory feedback, and that's a bit what I wanted to discuss about today, is the beautiful role of sensory feedback in parallel to, and in addition to everything that's based on CPGs, on coupled oscillators. And here, I don't know if you know, but eels are really amazing. So eels are these anguilliform swimmers. And if you make full transections of the spinal cord of the eel in one place or even two places, the animal can still swim and the locomotion is almost intact. So below lesion, you still have activity, rhythmic activity, and even that, not only that, it's even coordinated with what happens above, despite having full transection, no communication anymore with high part of the spinal cord and the rest of the brain. So here, it must be driven on sensory feedback. This keeping the rhythms active, keeping them coordinated is really likely based on feedback. And the most likely type of feedback is stretch feedback and pressure feedback, pressure on the skin. And that's what I'd like to talk about. So here, even for a long time, people know that feedback is really important. So you can easily demonstrate, for instance, if you take the lamprey circuit in the spinal cord, which is very well known, we know there are stretch receptors in the spinal cord. And if you feed them back into the system, if you don't feed them back into the system, you easily have trouble to cross non-steady state conditions like a speed barrier, as you see on the left. But if you add feedback, you have a local stiffening mechanism that allows this to cross it. So that's a bit the first thing you expect from sensory feedback, is to close the loop and help handle perturbations. But now what we're exploring is could feedback also help to generate the pattern itself and be a redundant mechanism to CPGs? So what we did is see how in our CPG circuit we could add, in this case, feedback from local pressure sensors that we know are locally going back into the lamprey network, and systematically explore what could the benefits of having that feedback into the system. And for that, we built a robot. We simulated muscles. We have sensors that can sense the interaction forces, and that allowed us to measure the local force left and right, and provide it to the local circuits to test what could be a beneficial effect of this local pressure feedback. And what we found out, it has a beautiful effect, really, really very nice to help generate swimming patterns. So I don't have time to go in details, but basically, by having the model, we could very systematically explore a circuit that's purely CPG driven versus some combination of sensory feedback into the system. So we could, for instance, remove coupling and still have feedback. We could even remove oscillators and just be purely sensory driven. Or we could explore the combined version, which we know exists in the real animal. In animal, we have both feedback, of course, and CPGs. And maybe one of the most interesting results we got is for this circuit here, when we removed all couplings between oscillators, like it's like an extreme spinal cord lesion. We still have the oscillators, but no coupling, direct coupling, and only the local feedback loops from the pressure sensors. And here what was exciting is that this leads to beautiful swimming. So really thanks to local feedback loops. So maybe look first on the video on the left. So on the video on the left, you see the decoupled oscillators, and there's no sensory feedback. So without feedback, now it's the same video, slow motion, there's no synchronization possible. Now, interestingly, on the right, by adding now the local feedback and still not having any coupling, you see a beautiful emergent coordination synchronization happening, purely due to the local mechanism. So it's really sensory feedback loops that now completely synchronizing the whole patterns and really replacing completely, in this case, instrumental coupling. And this was a bit of a surprise for us, because it's really embodiment being a key component and providing means of coordinating through local physical properties, and also providing the needed asymmetry to swim forward rather than stay on place. And this also worked on the real robot. So it takes a bit of time from random initial conditions. You see how the local feedback loop has, even if it's local, it has a global effect on the whole swimming pattern. And you see beautiful forward swimming thanks to the local mechanisms. And finally, what we did is very systematically explore different types of neural disruption that could in principle happen on the animal. So what happens if you kill sensors, if you kill couplings, if you even kill the local oscillators? Since we had everything there, we could very systematically explore, for instance, how the speed of swimming degrades when you do more and more neural disruptions. Just to give an example, if you're purely CPG driven, so no sensory feedback, if you start cutting couplings in the system, you become paraplegic or kind of very bad swimmer, because there's a lack of coordination. And therefore, the CPG circuit is very fragile against removed couplings. Now, similarly, if you are driven by sensory feedback to coordinate things, if you start disrupting the neurons, the sensory neurons, you're also very fragile. So here now, you see more and more disruptions, and the more you go down in the videos, the more the speed is being disrupted. So the decoupled circuit is also very fragile. And now, interestingly, if you put everything together, so the CPGs, the coupling, and the sensory feedback, then you start to be amazingly robust. So it's basically very hard to disrupt that. You have to really cut a lot to start seeing a disruption and a slowing down of speed. And this is really what we believe is happening in the eel and making the eel so amazingly robust. So once you have both the central nervous mechanism and the peripheral mechanism, meaning the feed forward and the feedback, you become super robust. And that's basically the take-home message, is there's a beautiful interplay between the central nervous system, giving the feed-forward component, and the peripheral nervous system giving the sensory feedback loops. And combining the two makes it more robust than having only of these mechanisms alone. So that's it. So basically, remember that CPG in principle can generate beautiful locomotion, but that local sensory feedback can really not only handle perturbation, which is the first thing you expect, but even much more. It can help to synchronize oscillators or even generate rhythms. I didn't have time to cover that, but you could even generate rhythms purely being on sensory-driven signals. And therefore, embodiment is really important, because I think we should see locomotion as the coupling of multiple mechanisms in parallel. Each are contributing, and it's hard to decode the respective role, but all participating there. And having them together really makes it amazingly robust thanks to redundancy. So it's probably why we have this multiple mechanism, is to be robust like the eel is robust. So still a few things to explore, like other sensor modalities, but basically the key word here, the take-home message, is embodiment is crucial here to understand this swimming. So I thought it would be a nice example for this community. So that's it. So thanks a lot for listening, and I'm happy to take questions later on in the chat and during the global discussion.
Excellent. Thank you, Auke. Just a quick question. Is there any learning mechanism, like explicit learning process going on in all this adaptation, or is it no learning at all?
No, there is learning, because the more people study the spinal cord, the more they discover plasticity. So the first type of learning you need is just tuning your frequency. So a small animal always has like an order of magnitude higher frequencies than a big animal. So you always need to tune to your body properties. And interestingly, we now have another project where we want to see how high parts of the brain can learn in the spinal cord space. So clearly high part of the brain doesn't have access to muscles. It has access to the spinal cord. And it's a very non-uniform space. So learning also happens higher above. And I think the spinal cord helps to do learning because it's a lower dimensional space than the muscle space or muscle fiber space. So we can come back to that in the discussion.
Yeah, that's a wonderful example. Yeah, thank you very much, Auke. This is a really, really exciting project, and you made a lot of progress in this salamander type swimming robots. Okay, well.